Hey everybody, now we're going to talk about multi-head self-attention. So in the last episode we looked at self-attention and we had an intuitive breakdown of this, of what the mechanism is actually trying to do. Now, multi-head self-attention is basically the same thing as self-attention, but it just performs self-attention head amount of times. So let's say we had 3 heads, it will perform self-attention 3 amount of times. The original transformer used 8 heads, which meant that we run self-attention 8 times over 8 different Qs, 8 different Ks, and 8 different Vs. Our final representation comes from the concatenation and projection of the individual self-attention outputs. So let's look at this individually, okay? So we have some input which would be below here, and what we do is we run here. There's we can see with the shadow that there's 3 heads, okay? So we have one projection that gives us Q, another projection which gives us another Q, and a third projection which gives us a separate Q. Same thing with K and V. Now we run dot product or self-attention over these first 3, for example. So we'll have 3 self-attentions running because we have 3 heads, okay? So we run self-attention for each one of the heads that we have. Then we'll concatenate all those head outputs together, and we'll have one linear projection, which will give us our Z, our final multi-head attention representation. Now, each head has dimensionality of D divided by number of heads. So D will be our model dimensionality. Let's say our model dimensionality hypothetically is 1024, and we have 8 heads. I can't actually, might be 128. That means that we, yes. So if we have 8 heads, each head is going to have a dimensionality of 1024 divided by 8, so 128. Okay, note that this has to be equally divisible, because what we're going to do is we're going to concatenate everything together. So if we have 8 heads, we're going to concatenate 8 representations together, so that should obviously give us D-dimensionality. And after that, we're going to project everything back. It's going to be projected from D-dimensionality to D-dimensionality. So this is why each head has to have the model dimensionality has to be equally divisible by the number of heads that you have. Okay, so we're going to code something up here. What we're going to do is we're actually going to code up a whole PyTorch class which will do our multi-head attention for us. So this involves reusing the scaled dot product attention that we looked at in the last episode, alongside how we can actually perform the projection of our inputs into the different heads. Okay, so here we're in examples MHA. Okay, so we're working with a PyTorch module here, and in the constructor we're going to specify our D model, so the dimensionality of our model, and here we've just said 4, and the number of heads. Here we have 2 heads, and dropout. So we work out our dimensionality per head, which is what we're calling self.d, and we do that by taking D and dividing it by the number of heads that we have. So that's this right here. Okay, we just perform some variable assignments. So self.d model equals d model, because we'll be using it inside of our class, and self.num heads equals num heads. We'll also initialize a dropout, which we'll be using at the just before we return the outputs. Okay, so here's the cool stuff. How do we perform this projection of Q, Ks, and Vs? And remember, we want to perform this head amount of times. We want to have head amount of Qs, head amount of Ks, and head amount of Vs. In this particular example, heads is 2, so we're going to have 2 Qs, 2 Ks, and 2 Vs. There's a couple of different ways of implementing this. This isn't an efficient implementation. This is more better for conceptual understanding. If we wanted to have an efficient implementation, what we would do is, well, I'll get into that after I run through what we're doing here for the Qs, Ks, and Vs. Okay, so fundamentally each Q, each K, and each V is going to be a projection. Okay, so we're going to learn the Qs, the Ks, and the Vs, and I spoke about this a little bit in the previous episode. So we're going from D model to D per head. And if we recall, in the diagram that I had, we called this capital D, which stands for D model, and DH, which you can interpret as D for head. Okay, so here instead of one WQ, we're going to have head amounts of WQs. Okay, so how do we do this? Well, we use a PyTorch module list, and then for every, for however many heads that we have, we're going to initialize that many number of layers. Okay, so here we have 2 heads, so we're going to have 2 linear layers which we initialize, and both of these are going to be D model times dimensionality per head. And we do the same for Ks, and we do the same for Vs. Now, if we were to do a slightly more efficient implementation, what we would actually do is I'll just do it for Qs for now, and we'll have a linear layer which would be D model also by D model. However, before we feed the inputs into our attention module, we would specify that we reshape this into the number of heads, right? So if we were to feed something in here, this would give us batch times time, so the sequence length, let's say, times D model. And then we would reshape this into something which is batch times sequence length times number of heads times dimensionality per head. Now, we're not going to be working with this. It's just slightly more confusing to understand than you know, just initializing 2 layers for each Q, each K, and each V here. Finally, we have a linear projection layer. So this represents this linear layer here. So what we're going to do is we're going to run our input through all of our Qs, through all of our Ks, and through all of our Vs. And then we're going to, for each tuple of Q, K, V, so for the first head, for example, we're going to run that through scale.product attention. We're going to do that for all the heads that we have, or all the representations over all the heads. Then we're going to concatenate them all together, and then we're going to project them through the linear layer. And this is that linear layer. Okay, so we ran through the scale.product attention in the last video. I will run through this again very quickly just so we can get to grips with the notation on the shapes, but let me do that when we actually call the function. Okay, so our model is going to take some inputs, and here we're calling this input X. Okay, so these will be this will be a tensor of batch times sequence length times D, the model dimensionality. So what does this mean? Well, we could have a batch of 4, for example. So each element in this batch would represent 1 sequence. Each sequence has a sequence length amount of elements in there, and each element is D dimensionality. Okay, so just to put an example on that, if I go back to this here, right? So this will be our sequence length. T is going to be our sequence length, 3. And for this toy example, the number of dimensions of our model is going to be 4. So we're going to have something, if we only have 1 element in our batch, so if this is the only sentence that we have in our batch, then we have this 1 sentence, 3 words, so this will be 1 times 3 times 4, okay? Because we have 3 words, we have sequence length number of words, which is 3, and each one of our sequences is represented in 4 dimensions. 1, 2, 3, 4. Okay, so this will be B times sequence length times D. Okay, so now what we're doing is for all of our inputs, we're going to project them with through linear Qs, linear Ks, and linear Vs. Okay, so remember, we have number of heads. So we have, in this case, we have num heads as 2. We have number of heads of linear Qs, number of heads of linear Ks, and number of heads of linear Vs. So for every linear, or for every Q layer that we have in linear Qs, we're going to project this. So we're going to call linear Q with our input. So here, our length of Q is going to be 2 because we have 2 heads. Same with K and same with V. So the shape of this will be batch times sequence length. So these first 2 dimensions don't change. And then our third dimension is going to be d divided by number of heads, and this is self.d here. This comes from here. So this is the dimensions that we have in each one of our linear layers, and this is and this comes from d model divided by the number of heads. Okay, so this here is dh, and then we have number of heads amount of each of these elements, right? So here we have 2 queues in this queue list, and each queue has batch length times sequence length times the head dimensionality. And same with k and same with v. Okay, what we're going to do now is initialize 2 empty lists. The first list is going to give us our output per head. So for every single head that we have 2 heads, we're going to get an output for it. It's also going to give us our attention weights per head in case we wanted to visualize them. Okay, so as far as shapes go, let me just collapse this so we can see this a little bit better. And I will just move this across. Doesn't need to be so big now. So for output per head, what we're going to do is we're going to have a list. So it's going to be a list of lists, or a list of tensors. In our list, each tensor is going to be of batch times sequence length times dh. So what we're going to do is we're going to use q, k, and v to run our scaled dot product attention. This will give us the output for one head, and we're going to have number of heads amounts of these outputs. Okay, and our attention weights per head, if we recall from the last episode, our attention weights are always going to be sequence length by sequence length. So, or not sequence length by, in matrix form, it's going to be sequence length by sequence length, okay? Because we have every word, and we want every word to pay attention to every other word, or we want to compute the attention value for each word to every other word in our sequence. So we're going to have batch times t, so every word, and times t. So this is going to be, this represents every word paying attention to every other word. And we have number of heads amounts of these. Okay, so what we're going to do is implement, we now have each one of these like linears and the shadows behind them. Okay, now what we want to do is take one set of this. So we want for the first head, we want to take this linear, and this linear. For the second head, we want to take that linear, and that linear here. And then we want to run scaled dot product attention for each of them. So we're going to zip our q, k's, and v's together, and this will give us the zipped variant, not the variant, but like it will take the first element of q, the first element of k, and the first element of v, and this will be the input to our first attention head. Or this will be, we will run scale dot product attention over these representations, which consist of what we're calling our first head. Okay, so let's jump into this. So the function takes q, k, and v. It's very similar to what we implemented in the last episode. Now, q is going to be batch times sequence length times okay, sorry, these are both going to be the same shape, so I will just change this to seqlen here, and we'll call this dh just so we don't get confused, and no, I'll just call this d by numheads. Okay, so that's exactly the same. I'm not sure why I left that in there, sorry. Anyway, so as we did last episode, we're going to we have our q, we're going to map model it with k. Now here we're going to perform a permutation. So right now k is, no, this is why I had it. Okay, so k is, they're all the same shape, so they're all sequence length by d by number of heads. But of course, if we have q, which is in, and ignore the batch dimension here, so if we just have q, which is in seqlen times dh, and k, which is in seqlen times dh. Now we can't multiply these two together because the this second dimension and this first dimension aren't the same. So we're going to perform a permutation. So actually we have batch and we have batch here. So permutation basically switches the axes, right? So here we have, this is axis 0, this is axis 1, and this is axis 2. What we're saying here is actually we want axis 2 to be axis 1 and axis 1 to be axis 2. So this permutation will end up being B times DH times seclen. And the mapmul operation will take just the last two axes to perform the operation on. So what we'll have resulting q.k or q mapmul k is going to be batch times seclen times seclen. Okay, so these DHs will is what the mapmul operation is going to be performed over. Okay, so we'll take our QK mapmul, which is batch times sequence length, and then we'll scale it by dividing it by the square root of D, which is the dimensionality per head. And we looked at that list in the last episode. We also looked at performing the softmax operation, what that does, actually giving us our attention weights, and matrix multiplying the two together to obtain our representations for the input X for this particular head. Okay, so the function returns output and it returns attention weights, which is what we see here. And then we the shape. So this is a for loop. So for every single head that we have, we got a Q for that head, a K for that head, and a V for that head. So we're going to get an output per head, or we're going to get an output for each head, and we're going to append it to this output per head list. Okay, so this is a tensor of batch times sequence length times DH, the dimensionality per head, and our attention weights per head, which is batch times sequence length times sequence length. So once this for loop is finished, if we have two heads, the length of this output per head list is going to be 2, which is where this times num head comes in. If we had 8 heads, then it's going to be 8. Okay, now we want to convert this list into a tensor. So what we're going to do is we're going to, for the output, we're going to concatenate everything across the last dimension. So basically we're saying, hey, look, we have this list which has 8 tensors in it. We want to have something which is the concatenation of every single one of the DHs in this list. So this would look like, if I just do this above the concatenation. Okay, so let's look at an example. We'll have example of the output per head. And this is a list of tensors, right? So let's, I wonder if I can do this. Nice. Okay, so what we're going to have is, let's tab this across. And if I do one more. So this is a tensor, and then we're going to have another tensor. Whoops. And we're going to have a third tensor. Okay, so inside this tensor we'll have something, let's say this is 0.0, 0.1, and this will be a tensor as well. So just making this easy to understand what's going on, or easy to read rather, because I know it's complicated to understand what's going on. Then this will be, let's call this 0.01, 0.00, 0.01, then this will be 0.10, 0.11, and we'll have 0.20, 0.21. Okay, so what is this? This represents one output head. Okay, so this will be one of these outputs. And then let's say we have 3 heads here. So what we're going to do is we're going to have 3 lots of these. So this will be 1. No, sorry, this will be 0. This will be 1, 1, 1, 1, 1. Let me just turn the light on for a second because I know the camera oops, ruined itself when it wasn't on. And then we're gonna have the same here, where we're gonna have apologies. We're gonna have 2, 2, 2, 2, 2, 2. Okay, so if we were to assign these shapes to actual numbers, here let's just say we have a batch of 1, so we'll just kind of ignore that. Our sequence length is going to be 3. Okay, so 1, 2, 3. We have our sequence is 3. Yeah, I don't know how to describe that a bit further. And our dimensionality per head is 2. Okay, so our model dimensionality is going to be 6. And because we have 3 heads, right? Just a coincidence that sequence length and number of heads is the same, but we have 1 head, head number 2, and head number 3, and each head has a sequence of 3 elements inside of it. Now, when we perform the concatenation, what we're going to get is, so currently this is, we have 3 elements in our list, 1 for each of the heads. That's this, this, and this. And what we eventually get into by performing this concatenation is B times seq length times model dimensionality. So the model dimensionality here is 6 because it's number of heads times the dimensionality per head if we were to reverse this operation. So here what we would have is something which is 0.00, 0.01, 1.00, 1.01. Let me bring that all on the same line just so it looks nice and neat. And then 1.10, 0.10, 0.11, 1.10, 1.11, and you get it. So for the last one, it will have 0.20, 0.21, 1.20, 1.21. Sorry, and I forgot that we'll have 2.00 here, 2.01. And the same thing here, so 1.10, 2.10, damn, who knew decimals could be so complicated, 2.11, this is 1.21, 2.20, 2.21, okay, so we've taken this, we've concatenated with this, we're concatenating it with this, and then we do the same for the second sequence, the second element in our sequence, and for the third element in our sequence. Okay, so this gives us batch is 1, so let's ignore that here. This gives us 3, which is our sequence length, times 6, which is going to be our capital D, our model dimensionality. Okay, so that's what outputs is. So this is example output. Now, attention weights, what we're going to do is, this is a good time to talk about intuition, about how to think of shapes in PyTorch, okay? So we have this example here, this is 3 by 6. So what does that mean? It means that in our matrix, we're going to have something which is 3 down, okay? We have 3 items. Now, each item is represented in 6 dimensions. So that means that every element for each item has 6 things in it. So 1, 2, 3, 4, 5, 6. Okay, so basically the last dimension is going to be the vector. So everything is a collection of vectors, but the last dimension indicates how big the vector actually is. What is the dimensionality of this vector? So if we look at this shape here, batch times number of heads times sequence length, initially looks scary to look at, but let's think about what's going on, okay? So here we have something which is sequence length times sequence length. So that means that each vector is going to, in our case here, each vector is going to, we're going to have something which is 3 by 3, okay? So if we drew something out which is 3 by 3, so 1, 2, 3. So this is our first dimension. We have 3 things, and each one of these will be represented by a number. Which is 0.0, 0.1, 0.2. Okay, 1.0, 1.1, 1.2. Okay, so and obviously 2.0, 2.1, 2.2. Okay, so the innermost has 3 dimensions, and we have 3 elements of these 3 dimensions. Okay, then we just kind of recursively apply that logic. Now we have number of heads, amounts of 3 elements, each of which have 3 dimensions. Okay, so if we want to expand that up into something which is 2 times 3 times 3, what this means is that we'll have a tensor, and this tensor will have 2 elements in it. Now each one of these elements will have something which is 3 by 3 in it. So 1, and if I just tab that along, so this will be our 0.0, 0.1, 0.2, and then we'll have 3 of these, so 1.0, 1.1, 1.2, and then we'll have 2.0, 2.1, 2.2. Okay, and we're going to have, so this is one head, so this is one of these 2s, and we're going to have 2 amounts of them, right? So we're going to have something else here, and inside of this collection we're going to have another 3 by 3 matrix. I guess this indicates the matrix or the tensor, whatever. Okay, and then we can scale that up again. So now we have number of heads of, or here we have 2 amounts of things which are 3 by 3. Now if we have another dimension on top, it means that we're going to have 2 amounts of things which have 2 amounts of things in each one of them, and each one of those contains things which are 3 by 3. Okay, so fundamentally the last dimension is, everything is still going to be represented in things which are 3-dimensional, but we just have a different amount of way, or we just have this hierarchical way of collecting these 3 by, or these I guess fundamentally 3 by 3 matrices, or 3-dimensional vectors. So here our attention weights per head is going to be batch times sequence length, right? And we're appending it to this list. So the amount of elements in this list are going to be the number of heads that we have. That's what this, that's how many times this for loop will actually run for the number of heads that we have. Okay, so this for loop is going to run twice with our number of heads equals 2. And every time it runs, we're going to append the attention weights, which are batch times sequence length. So the for loop running 2 times will have 2 things which are of this dimensionality. So what we're doing is, one, we're just stacking everything together. So that's a PyTorch operation just to change a list of tensors into a tensor of tensors. And then we're going to permute everything, okay? So as we ran through permutation up here, but it's a similar concept. So if after the stack we had something which was, after the stack, what we would have had is something which was num heads times batch times seqlen times seqlen. So I've done this times like right here with this asterisk operator to indicate the amount of elements in a list, but when things are in tensors, I'm using the actual x. So after we run the stack operation, what we would have is num heads times batch times sequence length. Now I think it's a lot more intuitive and quote unquote natural to think of things in terms of batch first. So that's what we're going to be performing here, where we permute this tensor to put the batch as the first dimension in the tensor and num heads as the second one. Okay, so we're going to have a batch number of elements, whatever our batch size is, that's how many elements we're going to have. And then for each element, we have number of heads operating on it, right? So we have 2 heads here. So each head is going to give us a different representation for our sequence. And that different representation is encoded in the sequence length by sequence length tensor. So after we perform the stacking and the permutation, we end up with something which is batch times number of heads times sequence length times sequence length. Anyway, to finish off multi-head attention, what we're going to do is we're going to project everything. Okay, so that's this linear layer here. So we've performed the concatenation of our outputs, and now we're going to project everything to align them back to a uniform representation. Okay, and that is done by this multi-head attention linear layer, which we initialize in the constructor. So after the concatenation, we have things which are in capital D dimensionality. That's D model in terms of our code. So big D is what we've called D model in our code. And we're going to just perform dropout on top of the outputs of this. Then we'll just return the projection and the attention weights. So let's take a look at actually using this. This is the toy examples code. So we'll just perform some imports. And what we're going to do is we're going to simulate an input. So here we have toy encodings, and that is batch times sequence length times dimensionality. So here we have 3 elements in our sequence. That's 1, 2, 3. And each of the dimensionalities of our sequence is going to be 4. So that's 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. Okay, and we have 1 element in this batch. So it's just to print that nicely for you guys. That would look like that. Okay, so this gives us our toy encodings, and then what we're going to do is we're going to initialize our multi-head attention layer, and this is going to be for dimensionality of 4. And number of heads is 2, so the dimensionality per head is what? Yes, 4 divided by 2, it is 2. And what we're going to do, we're going to call our multi-head attention layer and just print the outputs and the shape. So we're going to print whatever the projection here is. Okay, let me just expand this so it looks a little nicer. Okay, so our outputs are the same size as our inputs. Surprise, surprise. We're fixing the model dimensionality here. The sequence length obviously doesn't change, but everything we're working with in transformers will, between the layers, will eventually be something of D dimensionality. So 4 here. Okay. Some of these values are 0 because we have dropout, so we applied 30% dropout. This is something that they did in the paper, so I've just implemented that here as well. Anyway, so this and obviously we haven't trained the network. These are all random encodings, random initializations of our Q, K, and V network. And ideally, over time, the model will learn to create good representations for every Q, every K, and every V. Anyway, that brings us to the end of how multi-head attention works. In the next episode, we'll be looking at residual layer normalizations. It sounds a lot more complicated than it is, but it's actually quite simple, and it provides some stability for the training of the models. So I'll see you guys tomorrow. Bye.